Flat spiral spring method is used for determining Young's modulus, modulus of rigidity, and Poisson's ratio. It is divided in two parts: oscillations in vertical directions, as it is shown in the figure. Upper end of the spring is clamped while lower end is free, and small m dash is the effective mass of the spring, which is shown in the diagram. Capital M is the mass loaded to spring for the oscillations purpose. Capital M plus small m dash is the total mass oscillating to the spring. Capital N, that is the number of turns of the spring, which is given here, and capital T suffix 1 is a time period, and it is given how much time taken for 50 oscillations, and that is given in a second. Capital D1, that is the outer diameter of the spring, capital D2, that is the inner diameter of the spring, and mean diameter of the spring, that is capital D, is equal to D1 plus D2 divided by 2. Now find the radius of the spring, which is equal to capital R is equal to capital D divided by 2 in centimeter, and find radius of the wire of the spring, which is equal to small r in centimeter. T1 is the time period of oscillations, and eta is modulus of rigidity, which is given 16 pi square capital N into bracket capital M plus small m dash bracket complete into capital R raised to 3 divided by small r raised to 4 into capital T 1 square. It is shown in the observations table for oscillations in vertical directions. Mass in gram, number of observations 1, 2, 3, 4, 5, 100 gram, 200 gram, 300 gram, 400 gram, 500 gram, like this. If we are taking 100 gram into consideration, give the oscillations vertically. For 50 oscillations, what time is taken? 3 times take the reading and take the mean, that is small t. From that, find the period. Capital T suffix 1 is equal to small t divided by 50 seconds, and at last T1 square second square to be written in tabular form. So this is about the observations for oscillations in vertical directions. Now plot the graph. On y-axis there is a mass, and on x-axis there is a T1 square. Slope is equal to dash dash gram per centimeter square, and intercept on y-axis is equal to small m dash is equal to dash dash gram. Capital M plus m dash is equal to eta small r raised to 4 divided by 16 pi square capital N capital R Q into T1 square. So therefore from above, capital M is equal to nr raised to 4 divided by 16 pi square capital N R Q into T1 square minus m dash. This is like a equation for straight line, y is equal to mx plus c. From that, slope of the straight line is equal to m, and which is small m is equal to nr raised to 4 divided by 16 pi square capital N capital R Q. So therefore, modulus of rigidity eta is equal to 16 pi square capital N capital R Q divided by R raised to 4 into slope is equal to dash dash dynes per centimeter square. Now, how flat spiral spring oscillate in vertical manner, like this. It is just shown how it is oscillating in a vertical manner. It will be shown in the animation clip for oscillation in vertical direction at last. Now we will see about the oscillations in horizontal planes. It is observed from the diagram. There is one end of the spring as usual is fixed, while another end is attached with the bar having length capital L, and that is divided in x and x. Equidistant it is divided. Mass of each disc is m dash, and mass of bar is given capital M double dash, and length of bar is given there, and time period T2 is given small t divided by 50 seconds. As usual, upper end of the spring is clamped while other, that is the lower end, is free. M dash mass of each disc, M double dash mass of bar, capital L length of bar. This is shown in the diagram. This M dash, this M dash, this distance from center x, this distance from uh, center to this disc, and whole of this bar capital L is given here, and m double dash is a mass of this bar which is given here. See how that system oscillates horizontally. It is shown with the arrows in the diagram, and how distance changes like this, and take the oscillations after changing the distance from central point of the bar. Now take the observations in tabular form. Distance of each disc from axis x centimeter, and moment of inertia of the system I gram centimeter square. Note the time for 50 oscillations. T1, T2 second, T3 second, and take the mean, that is small t second, and find the time period. Capital T1 is equal to small t divided by 50 seconds, and find, that is the Young's modulus, capital Y, dynes per centimeter square. Moment of inertia of each disc is equal to m dash x square. Moment of inertia of a bar is equal to m double dash into bracket capital L square divided by 12 plus small r dash square divided by 4, where small r dash is a radius of bar, and it is very small as compared to capital L, that is the length of the bar. Hence r dash square, that is a small r dash square, is to be neglected. So therefore capital I is equal to twice capital M dash x square plus capital M double dash square divided by 12 is equal to dash dash gram centimeter square, and Young's modulus capital Y is equal to 32 pi square NIR divided by R small raised to 4 capital T2 square is equal to dynes per centimeter square. And from modulus of rigidity and Young's modulus, we can get Poisson's ratio, that is sigma is equal to capital Y divided by twice eta minus 1. So this is about flat spiral spring experiment for determining Young's modulus, modulus of rigidity, and Poisson's ratio. Animation clip for oscillations in vertical and horizontal direction shown further.